Welcome to the Vsepr formula video. This follows Lewis dot structures, and Vsepr stands for valence shell electron pair repulsion. And so what we're going to do is we're going to create some formulas, but we're also going to look at the geometry that's created when these valence electrons repel each other. A couple things that we need to pay attention to is the total number of valence electrons in a particular molecule. We need to be able to draw the Lewis structure, and we need to calculate or at least figure out how far apart can bonding and non-bonding electrons around a central atom repel each other. So if we look at BeCl2, beryllium has two valence electrons, and so if we place those guys on either side, that gives us our beryllium. And then we start with our chlorine, and we have 1, 2, 3, 4, 5, 6, 7 valence electrons. And again, we have another chlorine over here with 7 valence electrons. And what we get is we get this Lewis dot structure where we have this pair of electrons around beryllium, these two pairs, and to get them as far apart as possible, we actually get a structure that looks something like this, where the beryllium's in the center, and what's happening is these bonding pairs of electrons are repelling each other at 180 degrees. Over here we're actually showing a kind of electron density around the atom itself, and again we see 180 degrees between the two bonds. So if we have two valence electrons in a central atom, when they bond to two other things, they're going to tend to give us 180 degree geometry, which is, if we looked at this, this is also known as linear. When we go to something like aluminum chloride, again, aluminum has 3 valence electrons, so 1, and we could do it just a nice square Lewis structure. There's aluminum, and then we'll throw chlorine on here. 1, 2, 3, 4, 5, 6, 7. Again, 1, 2, 3, 4, 5, 6, 7. And our last chlorine. Again, the repulsion, if we look in 2D space, these pairs of electrons are going to push away from each other in all directions, and so we get this great repulsion between each pair. And what we get is we get a molecule that looks something like this. This one's laying a little bit on its side because in actuality the angles are all the same all the way around this guy. All of these angles in here, if the atom's on the outside, if that atom is equal to this atom, all those angles are 120 degrees. Okay, and this is called trigonal planar. That's its geometry, and its Vsepr formula is represented as a central atom, so A, and there's 3 things attached, so we would call this guy an AX, X, X, or we also know this as an AX3. So this is our Vsepr, if we want to know the Vsepr formula. That would be the Vsepr formula, is an AX3. Again, we're seeing the space filling of the electrons around those little bonds. If we go to methane, which is CH4, we have a carbon in the center. We have 4 valence electrons, so we spread them out around the atom. We put our hydrogens in, and this time hydrogen only has 1 valence electron, so we attach it, pair them all up. Now in 2-dimensional space this thing looks like it might be square, but you have to consider that we're going into a 3-dimensional space, and that some of these hydrogens that hydrogen might be pushed backwards, this one might be pushed forward, and so what we get is actually a 3-dimensional, kind of like there's 3 legs sticking down and a leg sticking up. And when we look at it with this object, what we get between all of these, because they're all the same atoms pushing away, is each one of these little angles in here is 109.5. And this guy, the Vsepr formula for it is AX4, and its geometry, all AX4s are tetrahedral. If we move to water, water actually, I didn't write my formula up here, but H2O. When we look at H2O, we have oxygen that's in our center, and oxygen has 6 valence electrons. So we go 1, 2, 3, 4, and then I'm just going to pair these last two like this. Now, this isn't the best Lewis structure to give us the geometry, because what happens is in the Vsepr formula, it kind of describes these pairs of bonding and unbonded electrons repelling each other. In other words, pushing each other away. And so, like in the tetrahedral, that we saw a minute ago, we had 4 things bonded. They were all pushing each other away. In this particular case, these pairs on top and bottom are also pushing, and what we get is actually what's called a bent shape. And so this shape here, we get a little less than 109.5 angle here, and we get this bent shape because there's these pairs of electrons sitting out here on either side that are driving those things down. And so the Vsepr formula describes the central atom, how many things are bonded, so AX2, those are my 2 hydrogens, and it also describes these pairs of electrons on either side, so it's an AX2E2, and that E describes a pair of electrons. This is also known as bent in the geometry. So moving on, we have ammonia, which is NH3, or nitrogen trihydride. So we draw our nitrogen. There's 1, 2, 3, 4, 5. Those are our valence electrons. Again, we put our hydrogens on. 1, 2, 3. Again, we have 4 pairs of electrons around the central atom, 3 that are in bonds, and 1 unpaired. So that unpaired is going to push those 3 hydrogens down, and you can kind of see it in this molecule here, because those pairs of electrons are sitting here driving each one of these bonds downward. And so it's not sitting planar, but it's kind of standing up. That nitrogen's kind of up in the air. And so this guy is a Vsepr formula is an AX, and you got 3 hydrogen, and you have a pair of electrons. So AX3E, and this is called trigonal. And it stands up kind of like a pyramid. So what we do is we call this guy trigonal pyramidal. Now there's a number of others, and what we're going to do is quickly look at these, and you guys will be able to look these up online or some other resource. But the first one that we already did is linear. And if you look at the central atoms, they help us out a little bit. That central atom is going to have 2 valence electrons. An AX3, the central atom is going to have 3 valence electrons typically. This particular atom is going to have 4 valence electrons, which is another bent. Notice we have this angle and that pair of electrons pushing it away. This is a tetrahedral, which has 4 valence electrons. If you look at this, you have a pair of electrons up top, and then you have 3 bonded electrons. This is going to tend to have 5 valence. You have 2 bonded plus 2 pair. This is going to tend to have 6, and so on as we move down here. This is going to be 5, 6, 7, and 8 valence electrons. Notice you're back to a linear, and this is going to have 6, 7, and this guy is going to have, the way to count it is how many things are bonded. So there's 4 things bonded. So there's 4, a pair, 5, or 6, 8. And then if we move over to this one, 1, 2, 3, and then 2, 4, 6. We're gonna. So we got 2, 4, 6, 7, 8, 9. Which we're gonna avoid this guy right here, and this one. We're gonna stay away from both of those. So it kind of gives you an idea of what the general shapes of all these substances can be. Notice the Vsepr formulas below them, and then also the description of what we've described in chemistry as the geometry.